The last subject I want to discuss about continuous functions is the intermediate value theorem. This actually is a pretty important theorem. It gets used a lot when you're proving other theorems. We won't be using it that much in this class besides in that theoretical standpoint, like when we're proving another theorem. I'll show you one quick application, which is kind of cute. But overall, this is something that is more of a theoretical result than something that you would actually do a lot of problems with. So, but it is it's a result that is very sensible, like it makes sense. And it tells you basically what continuity means on an interval, right? So though we defined continuity at a point, we also said if it's continuous on an interval, that means it's continuous at every point of the interval. So that's what they're using here. And in this situation, we're going to take a function f, and it's going to be continuous on the closed interval from a to b. So I'm going to just draw this, just to kind of illustrate what's going on. So here's, let's say, here's a, and here's b, and here's my function f. Okay, whatever, right? It's just a picture. So here's f of x. Now, if you look at what's going on here, here's the y value, f of a, and here's the y value, f of b. So what this statement says is, let's take n to be any number between those two y values, between f of a and f of b. Right? So let's say n is here. Right? Then, no matter which y value of n I choose, I can find a corresponding x value down here. So, like if n was here, the corresponding x value, which they're calling c, is down there. There has to be at least one, but there could be more. Like if I took n up here, right? Then I'd have 3 possible c's. It's okay. I can have more than one. The idea is just that such a c exists. Often it doesn't matter what c is. It's just we will use it because we want to know that such a c exists. So that's why I say it's a theoretical kind of result. You can see this isn't going to be true if I have a function that is not continuous. I'm going to try to draw like this. Well, see if I took like something like this, I cannot find a c for every value of n, right? Say if I have anywhere here, I'm not hitting the function, right? So I can't find a value. There's no f of c that equals n. Of course, because I picked one in the gap, right? But if the function is continuous, you will always be able to find a c. So that makes sort of intuitive sense, because if I'm going to go continuously from A to B, I'm making my curve, I'm not picking up my pencil, right? Or my chalk. So somewhere in there, I'm going to go through each of those y values. And of course, I drew both of these going up, but it's true as well if they're going down, right? So you don't necessarily know whether f of A or f of B is bigger, but it's just that n is between them. So that's the result. We can find a proof in the extra materials or in Appendix F of the book. I'm not sure to what extent it's really that important for you guys to prove this, so it's there if you're interested. We have one quick kind of sort of cute application of this intermediate value theorem. Okay. And that is a problem like this. the equation natural log of x equals x minus root x on the interval 2, 3. Okay, so you can think of this, right? A solution to the equation is between the left-hand side equals the right-hand side, or we can put everything on one side and say that that equals 0, right? So here's what I'm going to do. I'm going to write ln x minus x plus root x equals 0. So I'm rewriting my equation in that form. Now, if I call this guy a function, f of x, that's going to be my left-hand side. ln x minus x plus square root of x. Finding the solution to this equation, or showing that there is one, is the same as showing that f of x is 0, or showing that f of x has a root in my interval, right? So I want to show f of x has a root in 2, 3. Okay, now the intermediate value theorem tells me that I have to go through every point, right? So if one of these, not those, but if I've got f of 2 and I've got f of 3, those are the y values, right? If one of them is positive and one of them is negative, then somewhere in the middle, I've got to cross the axis at least once, right? The y, yeah, okay. So let's check that out. I'm going to plug this stuff in there. ln 2 minus 2 plus square root of 2. And because I don't want to bore you by watching me not know how to use a calculator, I did it on my own time and brought it on a piece of paper. So that is that number. The other one is this number, right? So because the first one is positive and the second one is negative, by the intermediate value theorem, somewhere in the middle, there's going to be a 0, right? And you can always write IVT for intermediate value theorem, that's fine. Somewhere that f of x, and that it would be called f of c, but what is called f of x equals 0. And that's all that you need to do. Now, of course, this doesn't help you find the root. It just shows that the root exists. So the question is why do I care? Well, let's say you actually had to solve this. I mean, this is not one that you can solve just with algebra, right? That would be terrible, right? Or you get rid of this, or you get e to that, and there's x's and e to the x. It's not nice. No, you don't do that. So if you really had to solve for a root, and if you had to do that for some application, you'd just do it numerically, right? You'd take this guy and you can solve with Newton's method, whatever, you can solve bisection method. There's all these different methods of finding roots because that's actually really an important thing to do in different cases. But very often you need to start somewhere to find your root. You need a interval to start out with to make sure your method will find something that really is a root, because that with numerical methods sometimes that happens, that you either doesn't converge, you don't find a root, or you find something that isn't really a root. It depends on the method. There's a lot to say about that, but it is important to know where you're starting out, and if you start out with something that has a root in it and use your method, you should be good to go. So it is actually important to know that there's a solution inside a particular interval, even if you can't immediately find that solution, because knowing that knowledge will help you at least calculate it numerically.